Half of our block on Wednesday, we talked about Lewis structures. Now, this is going to take us a little while to get good at, but we need to start talking about Lewis structures. Now, Lewis structures are really a way of representing valence electrons, and you may or may not remember how to count valence electrons, so let's go to a periodic table. For example, if I look at nitrogen, and here's nitrogen, let's make it a little bigger. Okay, so here's nitrogen here, right? Well, nitrogen has in its valence shell, you might remember that this is the n equals 1 level, right? N equals 1. It's the first energy level. And then this represents, ooh, hey, crazy, represents the n equals 2. So n equals 2. And so this is like right, the 2p sublevel, sorry, 2p, the 2s sublevel. I should actually listen to myself instead of just talking. And this is the 2p sublevel. And if I want to count up the valence electrons, I can simply count from left to right, right, along an energy level. So 1, 2, 3, 4, 5. And so nitrogen will have 5 valence electrons because it's the fifth over within its row. Remember that I never count the d electrons because if I look at this sublevel, this is the 4s, right? These guys, however, are the 3d sublevel. And then back over here is the 4p. So I'm only going to be counting the electrons in the S and P block. So I'll start at the left, skip the D block, and then continue counting in the P block. So if I wanted to look at, say, bromine, for example, bromine here, I would count 1, and then 2, and then 3, 4, 5, 6, 7. So bromine would have 7 valence electrons. And so we can count valence electrons from the periodic table. I'm going to erase all this junk so we can look at this later, get something more coherent out of this. Okay. But here is our clean periodic table. And we know that nitrogen has 5 valence electrons. So let's look back at this guy. And we know nitrogen has 5 valence electrons. So I'm going to put nitrogen here. And I'll put dots around it to represent the valence electrons. But my dots are always going to either go on the top, the bottom, the left, or the right. So I'll start and I'll just put 1 there, and then 2, and then 3, and then 4, and then 5. We always sort of alternate where we're putting the dots as if we were filling orbitals following Hund's rule, right? But it doesn't really matter. We just need 5 dots around here. Okay, so that's nitrogen. Well, if I were doing N3 minus, I could also draw a Lewis dot structure for it. Now that's an ion, and N3 minus is N that has gained 3 electrons. And you might say, how is it gained 3 electrons if it's 3 minus? Well, remember, electrons are negative. And so to become 3 negative, you have to gain 3 extra electrons. Well, if you started with 5 and you gained 3, now you have nitrogen with its same 1, 2, 3, 4, 5 electrons, but it's gained 3 more. So 1, 2, 3. And now it has 8 electrons all the way around it. It has 8 total electrons. But because it's an ion, I'm going to put a bracket around it like this. And I will put a 3 minus next to it to show you that it is negatively charged. Okay, so we're going to be doing Lewis dot structures for the remainder of these atoms and ions. And you're going to notice some patterns for ionic compounds, or for the ions that are formed, either the cations or the anions. That's what I'm trying to say. All right, so let's do something useful with this. One thing I wanted you to notice is that if I have a metal and a non-metal, like suppose I have NaCl, right? We know that NaCl is formed when you have sodium metal reacting with chlorine, right? Well, if we were to draw out the Lewis structures for sodium metal has one valence electron, right? So we'll draw one valence electron. Chlorine has 7 valence electrons, so 1, 2, 3, 4, 5, 6, 7, right? Well, if sodium were to donate this, right, over to chlorine, all of a sudden I would have Na, and it would have no valence electrons at all, so I would put it in brackets, and I would give it a plus sign, right? And I would have Cl, and Cl would have 8 valence electrons at this point. Except that's one more than it usually has, so I would put it in brackets, and I would give it a minus sign. And if you look at this, this has a full valence shell. This has its full valence shell. And usually we would say that this looks empty. But if you recall, that just means we have emptied it down to its full valence shell below. So both of them end up with a full valence shell. It's just that one is the electrons that used to be inner electrons, and one is just adding to its outer shell. Okay, so yeah, so they both end up like this. So this is an ionic bond, and this makes sense in Lewis structure term because you can see that this one is empty and this one is full. It fits our pattern of having full valence shells for stable ions and compounds. But what do we do for something that is covalent? Well, it turns out that for something that's covalent, we're going to share electrons. If I have oxygen, for example, it only has 6 valence electrons, right? Another oxygen has another 6 valence electrons. Well, there's no way I can donate. If I donate the 2 electrons this guy needs to have, right? If I donated these guys, right? This guy on the right ends up with 8 valence electrons. It ends up pretty happy. But this guy ends up with 4, and that's not good. So this doesn't happen. No way. So instead what we're going to do is we're going to share electrons. And we're going to come up with a system for it. But when we look at this, oxygen ends up sharing 2 electrons each, right? And they're in between. These shared electrons mean that we can count as if oxygen now has 8 total electrons. So this guy has 8, right? It has 4 shared and 4 unshared. Well, this guy has 8 total also, right? It has 4 shared and 4 unshared. So they both end up with full octets, but they can't separate anymore. If you look at sodium chloride, the sodium and chlorine are completely independent, or can become completely independent. For example, when I dump salt in water, the ions completely separate. When you did double displacement reactions, we used that as the basis for rearranging the ions in a double displacement reaction. However, molecular compounds cannot separate because this oxygen, if it wanted to leave, would be leaving behind the 4 shared electrons and it would no longer be particularly stable, right? Or it would take those 4 electrons and this guy would be not particularly stable. So this O2 always stays as one unit, one molecule. So another name for covalent compounds is molecular compounds because they always stay as one unit, one molecule. Okay. Now, one thing I want to get from this is that those shared electrons are drawn as dashes, and dashes are equal to 2 shared electrons. Okay. So 2 dashes is, right, 2 dashes is 4 shared electrons. Okay. Just to give you a heads up on the notation. So this is kind of convenient. Whenever you see a dash, those are shared electrons. When you see dots, they are unshared electrons. Nonmetals always are going to bond and form full octets, except for hydrogen. Hydrogen, if you'll recall, is in the first energy level, and so it can't form an octet. It fills its energy level with just 2 electrons. And so hydrogen forms 1 bond and it is done. 1 and done. Okay? That tends to be hard to remember for you guys because you get so in the habit of putting 8 electrons that you want to put 8 electrons in hydrogen. But unfortunately, it just doesn't have room for them. All right? Now, if we look over here, we've got we're going to practice drawing covalent bonds. And I want to set up sort of a system for it. You can do this by trial and error, but I want to set up a system. And the first thing I want you to do is count the valence electrons. Count valence electrons, okay? Please count the valence electrons. So when I see Cl2, for example, Cl2, well, that's the same thing as 2 Cls, so that's 7 plus 7. Right? Again, if you recall, chlorine is over here, so it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So 7 valence electrons for chlorine, because it's the 7th element over. So 7 valence electrons. Right? So if we were counting over, 1 for these guys, 2 for these guys, 3, 4, 5, 6, 7. And then noble gases would have 8. All right, so 7 for each chlorine. 7 and 7, that's a total of 14 electrons. 14 electrons. Okay. The next thing I'm going to do is draw a skeleton. Draw a skeleton. And when I say a skeleton, I just mean draw single bonds. I don't mean like, ooh, spooky, it's a skeleton, right? Instead, Cl, 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 right? Right. Ooh. Draw a skeleton. Ooh, getting good with the clavicle here. Socket joint, a little humerus. Radius ulna. It's too small. Carpals all look alike. And phalanges. All right, you get the idea. Here's my skeleton. Draw a skeleton. Anyway, first we draw a skeleton. We just use single bonds. Okay, so Cl bonded to Cl. However, we're going to then fill it out. Right, 3 is fill in octets. Okay. Now, I don't care about how many electrons I actually have at this point. Just fill in octets. You'll see why. Fill in octets. So here are 2 electrons, right? These are 2 shared electrons. Well, that's 2 on the right of this chlorine, so I'm going to put 2 on the top. I'll put 2 on the left, and I'll put 2 on the bottom. Again, on this one, I'll put 2 on the top, 2 on the bottom, and 2 on the right, because I have 2 on the left of it. So this is full octets. Everybody has 8. If I count the total number of electrons, I always count with 2 fingers. You can't see, but I'm pointing 2 fingers at these 2 dots and saying 2, 4, 6, 8, 10, 12, 14. And so this is 14 total electrons. Right? So the fourth step is compare the E minus in your structure right, to your valence electrons. Right? And if you look, I have 14 and 14. That's good. These are the same. Check. And we have full octets. Okay. Check. So this structure is done. If we have the same number as the valence electrons that we counted, and we have full octets, that is a good structure, and we are happy. Okay. And so this system works really well. Right? So Cl dash Cl dot 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 dot. But what do we do if it doesn't work? Right? What do we do if it doesn't work? Well, let's try that. Let's try that. Let's see what we can do. Well, let's erase some junk. Let's see if we can't make this thing happen. Should be an easier way to erase in Cami. There probably is, and I just don't know what it is. Let me get rid of this skeleton. It's too spooky. Leave a mess there. So we erase and we erase and we erase because we care. There we go. All right. So let's try S2 then. Let's try S2. And if we do S2, well, S2 has 6 plus 6, 12 electrons. Okay. And again, I refer you to our periodic table. S is in the column that has 6 valence electrons. Okay. So 12 valence electrons total. So I'm drawing my skeleton, S, S. And I'm going to fill in my octets. So here's my skeleton with its full octets. Now, since it's a skeleton, it only has a single bond, and it's got 2 atoms, and it's got full octets. Again, I have 14 electrons. Now, this is a problem, because this is too many. It is 2 electrons, too many. Okay? 2 electrons, too many. What do I do? Well, I need to reduce the number of electrons. So I'm going to tell these poor sulfurs that they're going to have to share a little more. And so let's look at it. So let's put a second bond in there. If I put a second bond in there, I'm going to put my full octets again. And this is 2 4 shared electrons, so I'll need 2 4 unshared electrons. 2 4 6 8 gives this guy an octet. 2 4 6 8 gives this guy an octet. So now we have a second bond in there. Let's count the electrons. 2, 4, 6, 8, 10, 12. This is 12 electrons. And so by adding a second bond, right, for every extra bond we add, we get rid of 2 extra electrons. And so since I was only 2 away, I only had to have 1 extra bond. Okay? And so now we have full octets. Check, right? We have the right number of electrons. Check, right? 12 equals 12. And so now we're at the proper structure. So S double bonded to S with 4 unshared electrons on each sulfur. And there it goes. So you now have the skills to draw Lewis structures for the other ones. Okay, and that is good. And if you feel really confident, what I'd like you to do is realize that the directions for the Lewis dot structures are laid out specifically right here. There's this really nice sample problem right here. And there are practice problems here for more complicated structures. Now, these have more than 2 atoms. So you're going to have to put an atom in the center. Okay, we're going to put the least electronegative element in the center. So if I have SiO2, we're going to put Si in the center. Okay, and we'll put our skeleton with oxygen on either side. Okay, so that's what we're going to do with this one because it's more complicated, right? We still have to count up valence electrons. Well, sulfur is 4, silicon is 4. And 2 oxygens, right? Oxygen is 6. So that gives us 4 plus 6 plus 6, which is 16 electrons. Okay? And this is oxygen is 6, but we're going to multiply it by 2, right? So however you calculate it, you need to add up the total valence electrons and get 16 electrons here. If I fill in my dots, right? 2, 2, 2, 2. I now have full octets, and you think, oh, great, I'm done. Well, no, I'm not, because 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This is 20 electrons. Well, I only have 16, so I'm off by 4 electrons, right? 4 electrons means I have to add 2 bonds. And so what I'm going to do is I'm going to add a second bond to each oxygen. And then I will fill out my extra dots, my octets. This oxygen has 2, 4, so I'm going to add 2, 4 more. Now it has 8. 2, 4, 6, 8. This silicon has 2, 4, 6, 8 already, so I won't touch it. And this oxygen has 4, so I will add 4 more. And if we count the total, 2, 4, 6, 8, 2, 4, 6, 8, 6, that's 16 electrons. Oh my gosh. And so that is done. Okay? So there is one of the more complicated ones. That should be enough to give you a good start at drawing Lewis dots. I would really recommend, if you're doing this, to read the whole of this page, because it really explains it, and it gives you these nice tips down here for drawing Lewis dots. It's only one page, but it is brilliant. All right. Why I didn't get the Nobel Prize in Lewis dot directions, I do not know. All right. But either way, at this point, you should be getting close to finishing this second page of Lewis dot structures. Okay? And that's where we are at the end of Wednesday. Thank you.